Um, Hi everyone, welcome to my channel. Um, Today we take a moment to remember Peter Higgs, who recently passed away. Um, Peter is known for his idea of Higgs boson. Um, he and this contribution, his contribution to the physics and science in general was immense, uh, which he unraveled to which he uh, contributed to unravel one of the biggest mystery of modern physics, which is where do the particles get their mass. Uh, so prior to 1960, how do particles acquire mass was a rather puzzle. People didn't know. Um, and in 60s he proposed the idea that in all the space a, a, a field permeates, and with interaction of the particles with this field, the particles acquire their mass. So he proposed this idea, and people were actively looking into this idea, uh, and experimentally verify this idea. And it took almost a decade, more than a decade, before LSC at the CERN, Large Hadron Collider at the CERN, uh, announced the discovery of Higgs boson in 2012. And so, following that, in 2013, he was awarded a Nobel Prize. Um, Now, his discovery of this boson, Higgs boson, uh, earned him a place alongside of Einstein and Newton. So this discovery was very not only groundbreaking, but it also was a revolutionary idea in modern physics and modern science. Um, to put his contribution to the context, um, we have to start with some historical background and the development of the physics in general. Um, so from time immemorial, uh, people ask this question: what is the things around made up of? What is this universe is made up of around? Um, what are the constituent? What are the indivisible ultimate fundamental particle? This question was asked long time ago, and people search answer in many ways. Um, in particularly the idea this got popular in Western science when people like Dalton's proposed this idea of uh, atoms and molecule and things like that. Um, and then Rutherford came with his gold leaf experiments. So the search for the indivisible fundamental particle that makes up the universe was uh, people were pursuing these ideas, and in that course, people came up with molecules. Um, the the idea was that when you zoom in at the particles or matter, for example, take a water. If you zoom in and zoom in and zoom in, uh, is the water is still continuous? And the answer was found that no, they are made up of little uh, particles jingling around, and those were the molecules. And then the question came, what are those molecules made up of? And the again there was the atoms and atoms combined to make molecules. So again the question came, is an atom indivisible and fundamental particle? And the answer turned out to be no. Uh, the an atom has its structure. It consists of electrons, which are whizzing around in orbit in outside, and at the central core there's a nucleus. Um, and then people started looking into the nucleus. Of course, the electron turned out to be one of the fundamental particle, uh, and but people still looked into the core, of the nucleus of an atom, and they find out it's a proton and neutron. It's mainly made up of protons and neutrons. So, and then again, are protons and neutrons the fundamental particle? And it turned out that it's no. Protons and neutron also um, have structures. They are made up of something fundamental particle called quarks. Uh, Now, with this electron, protons, and neutrons, and discovery of quarks, then we have the understanding of the fundamental particles. This is famously known as uh, standard particle, standard model for particles. So the characteristic, the defining properties of our current understanding, current model of uh, uh, the standard model is that the particles in general are classified into two broad classes. One that make up that constitute the matter of the universe, which are mainly known as leptons, and the others are force carrier particles, which are called boson. The examples of fermions would be electrons and quarks. Uh, the force carrier particles would be boson. The main difference in them is that the fermions have spin, uh, half spin, um, the fractional spin, and then the bosons have the integer spin, like 0, 1, 2. So now the electrons is orbit around the atom, and at the central core, in nucleus, proton and neutron reside, and these are made up of quarks. Now, what binds the protons? Because proton have the same positive charges, and they should be repelled by electromagnetic force. Electrical force is repulsion because the same charge is repelled. But why aren't they? So what holds them together? So there are mainly four kind of forces in nature. That is, one is strong force, uh, weak force, electromagnetic force, and gravity. Well, we do not treat. We sort of try to neglect this gravity in the standard model of particles because it's nearly negligible on that scale. Um, so it was found that the at the nucleus, the proton and protons are held together by a very strong force, called strong nuclear force. And the bosons, there are again two kinds of bosons. One is vector, one class of boson we call vector boson or gauge boson, uh, and the other Higgs boson, which is responsible assigning mass to the particles, and which is the main contribution of Peter Higgs that this life is mainly about. Now, the mediated particles or the bosons, they mediate these protons and neutrons at the nucleus of the protons, and the and the weak forces contribute in weak forces like in radioactivity. These weak forces carriers and W and G bosons contribute to these inverse decay processes where neutron turns into proton, and this is very important process, and that actually powers the sun, without which the hydrogen do not fuse to helium. This is one of the important processes to power a star. Ultimately, this is a source of energy for us, and the carrier for electromagnetic force is a photon, which is massless. Remember the strong forces, which is gluon, the strong force carrier, mediator particle, and massless, the electromagnetic force uh, carrier, which is photon. Both are massless particles, but they mediated these forces. Uh, but the weak forces, uh, W and G bosons, are massive particles, and they mediate weak forces. And again, which is the example is radioactive decays. So this is the current understanding. Besides these quarks and electrons, and there's a neutrino. Uh, these are very small, tiny particles. Uh, so every second, trillions of uh, neutrinos pass through us, but we hardly uh, are aware of them. We don't even know them. So they are very, very tiny, and they instantly fly with the near speed of light. So, but they are important aspect of the standard model of particle physics, and these are again these are only responsive to the uh, W and G bosons, which are nuclear um, weak forces carriers. So and now there's very puzzle that the mass, the total mass, if you well, the the nucleus consists of protons and neutrons, and a proton and neutron made up of three quarks. But if you the mass of a proton is way larger than the constituent quarks, like up and down quarks. So if you add them, these quarks, the mass of um, the proton is way larger than the added mass, the combined mass of three quarks. Now, this was at that time was quite puzzled. Then how is it possible that proton has a larger mass than the sum of its constituent particles? This was a big mystery at that time. But this is not the part of the Higgs boson. It turned out later that, but it might have started the mass mystery, the question that how do particles receive their mass? How do they acquire this mass? Uh, and as I mentioned, this Higgs then proposed this idea is that the all the empty space around us is permeated by a field, a scalar field, which is now known as Higgs field. And any interactions that the particle interact with this Higgs boson field, and acquire mass. Um, well, I know this is a bit of confusing ideas, and not quite intuitive, but the famous analogy is that let's imagine there's a party, people are drinking and talking, and there's a bar. So if an unknown person wants to go to the bar, then he can easily find his way and go to the bar because no one knows him. He's not famous. He can go. But if famous person, a celebrity or somebody, tries to walk through the people, a crowd of people to get to the bar, then he or she will be surrounded by many people. This is like interaction with the field, and this is how, uh, meaning the celebrity, or the famous person gets massive. um, so this boson field offers a drag to the particles, and the more drag it gets, the more massive this thing is. So that was the interpretation of proposed by Peter Higgs, and one of his prediction would be the discretization of this field, which would be Higgs boson, and people started looking for this, searching for this particle, Higgs boson, for years and years, and then found finally, in 2012, the LSC, Large Hadron Collider, at the CERN was able to find this particle, and it was announced in 2012, in 2013 he was awarded uh, uh, Nobel Prize. Um, so he helped unravel to solve one of the biggest puzzle of the uh, of modern science. Where does the mass come from? But again, I would like to emphasize one thing is that most of the mass does not come from Higgs field. Okay, only 1%, a small fraction of mass comes from the Higgs boson. The rest of 99% mass is in the form of the energy. Okay, let me a little bit explain this. Where is the mass? I was earlier telling about this. How is the mass of a proton is larger than the masses of these constituent uh, quarks. So if it happens that a the inside a proton there are three quarks, and which are bound by this gluon, this boson named gluon. So it is responsible to binding in these three quarks together, and this gluon are massless and nearly travel with the near speed of light, and they strongly um, hold these quarks together. Now, imagine what happens if you try to separate out one of the quark from them. Um, it opposes, like spring restoring force. It will not let it. It will not let it break the combinations of three quarks. So, but if you apply more and more energy, then there are the creation of antimatter, and still the structure would be preserved. So bottom line, these gluons are like exchanging informations between quarks, and in a high speed. So uh, this energy of these gluons actually carry a lot of energy into it in them. And by famous E is equal to mc squared by Einstein, you can convert this energy into mass, and that's where the most of the 99% is mass is stored in an atom, nucleus, let's say, or proton or nucleus. So, but still, Higgs boson or the mass derived from Higgs boson is quite important, because remember I talked about this mm, inverse beta decay process, in which the neutrons convert into uh, protons with ejection or emission of electrons and anti-neutron. And the slight difference in the masses between the protons and neutrons, it is crucial to happen this kind of process. Uh, the other thing we can think about that, if there is no such processes, then there's no possibility of having atoms. Uh, and it contributes it significantly to making constitute an atom. And even if it's 1%, it contributes to the creation of 100% mass of the universe. So it is still a very important process. But again, having said that, uh, most of the mass is contained in proton is actually in the form of the the energy of the gluon, which is exchanging informations between quarks. Um, so this is the status of the uh, modern standard particle physics, and where Peter Higgs played an immense role to find out where the mass comes from. Uh, and there was a key piece of this particle physics, standard model of the particle physics, but there the model has some problems. Also, it's not complete yet. People are looking into it more. Um, for example, one of the question that standard model cannot answer is that why there are more. So, according to the standard model of particle physics, there should be an equal number of particles and antiparticles. Now, we have seen particles or matter, but where is the um, antimatter? So the question is, why do not see the equal amount of matter and antimatter? This is a great puzzle, which the standard model of particle physics does not offer any answer. Uh, Similarly, there's a uh, the graviton. There's a like gravity field. There is a particle, the discrete particle, which is named as graviton, but we don't understand graviton that much. So it is still a puzzle. So people are looking into beyond this standard model of physics, uh, which is very successful uh, theory in explaining, together with quantum mechanics, explaining the understanding of the universe. But we were still exploring more. Um, so I think so. This live, we would like to pay tribute to Peter Higgs, who died on April 8th, which is the day before yesterday. Uh, and his because of his contribution to science and physics is nearly as equal as the contributions of Newton's and Einstein. Um, well, that's all I have to say for today. Thank you for tuning in. So see you in the next live. Please share and subscribe. Uh, so bye.